Hello everyone, my name is Chen, and I'm proud to present to you my final project for CS186. As you can see below, my team includes me, and that's right, also me. And this is because I'm the only member left in my team, as everyone else has previously dropped the class. There are hundreds, if not thousands, of dog breeds in our world today, and it's often tedious to memorize all the different breeds of dog in modern society. Because of this, I thought it'd be a cool project to create a neural network and use computer vision to be able to match dogs to their own breeds given a picture of one. This represented our minimum viable product, but we also had means of creating an Android app for users to use on the Play Store as well. All machine learning has some sort of algorithm at its core. Gradient descent is an algorithm used when training a machine learning model. It uses calculus to iteratively adjust values and parameters to minimize a cost function. To picture how this algorithm works, we can use a bowl for example. The bowl acts as a plot for our cost function. The bottom of the bowl represents the best set of coefficients and parameters to run an ideal algorithm for best results in machine learning. The goal is to try to repeat this practice over and over with different values and try to find the lowest cost possible. Although there are a lot of parameters that go into making an algorithm ideal, learning rate is probably one of the most important and easiest to explain. Relating back to the example we used before, the arrows that you see are trying to reach the local minimum in the convex area representing the bottom of the bowl. In gradient descent, our learning rate helps us determine the size of the arrows that we're using. The learning rate is set between 0 and 1 normally. The higher the value, the bigger the arrows. An ideal learning rate can neither be too high nor too low, as seen in the example below. Too high of a learning rate, you may never reach the local minimum. Too low, and it could take too long. To make my models, I use Keras, a deep learning API designed for Python. Within Keras, you need to pick an optimizer which serves as an algorithm that you were programmed to train itself. On the graph below, you can see the cost functions of the most commonly used optimization algorithms. I chose to go with ADAM, which stands for Adaptive Moment Estimation, to compute adaptive learning rates for each parameter in my model. ADAM starts off taking large steps in reducing our cost function and slowly plateaus out into later iterations. ADAM requires low amounts of memory and ran quite smoothly on my device. Another optimization algorithm I chose to test out was SGD-Nesterov. SGD stands for Stochastic Gradient Descent. This algorithm, while tested to be more consistent than ADAM, uses up a lot more time and resources, as it takes much smaller steps in reducing its cost function compared to its counterparts. In tests, however, ADAM was actually able to outperform Nesterov in both time and accuracy on my datasets. The framework of my project has two main files containing the needed code: the test file and the train file. The train file pre-screens the data and loads a sophisticated model to run its test iterations. The test file is used after the training has been done to load pictures in order to see if the neural network actually works as intended. Our test results are then stored in one of these 4 folders depending on how good the results are, along with which the algorithm was used. Our testing and training pictures are actually stored separately in these 2 folders, as you can see. Here's our testing, and here's our training. Along with that, our labels and annotations for the dataset are also included here. Hello everyone, now we're going to take a little more in-depth look at our code. This is of course the training file, so I have the training file and test file. These are both running Jupyter Notebook. We've imported all of our libraries here, and we have all these functions up here to just kind of help us through. We have some things for parsing data sets, reading in images, and just helping to build our model. So the pre-screening happens when our images are first read in. This read image file, for example, takes the image through CV and basically resizes the image to exactly how many pixels by how many pixels that we'd like it in, just so every image is consistent throughout to work with. The main part of the code happens right here where I've highlighted. Here we're basically just looking at paths. You can basically input any data set you would like as long as you fix the path, and the algorithm should still work. Here we're looking at just creating the IDs for all of our images through that large spreadsheet I showed earlier, and here we're just splitting the data set, and the parameters come into play right here. The parameters mainly are put into the model, so we can tell the program exactly what we want the model to do. And for example, the epochs here, how many iterations we want, and the learning rate is just how fast you want the model to learn, similar to the arrows that we talked about earlier. And the batch is simply the number of training examples in each iteration. So here is where we define what our optimizer is and what algorithm we want to use. So we build our model with this function right, or with this command right here, and then after that we're running the atom optimization, and we have our learning rate here, and we're just going to compile our model after that. So the real training comes back here. We have our callbacks in place, and basically through these training steps we validate our model, and we basically input all of our parameters. Right here I have a test that I recently ran. Of course I won't run this on live because this number of epochs usually takes my computer probably around an hour to run. But as you can see, first of all, the val loss improves every time based on our model. So throughout the first iteration, the value loss, which is also equivalent to the cost function, basically improved from infinity to 4.539, etc. You want your val loss to be as small as possible because that represents the cost function. The lower the cost function is, the more accurate training will be. And as you can see, since we used the atom optimizer, it took pretty big steps to begin with, going from 4.3 to 4.1, kind of tethering off towards the end where the steps were pretty small, went from 2.97 to 2.92 as you can see. And I kind of didn't think there was any need to run more epochs than 20 here, as you know, it went from 2.74 to 2.73. I thought the steps were a little too small given how much time I needed. So after the training, we're going to go to the test right here. A lot of the same code as the training. We're going to read in the images, resize, and here we're basically taking the same code, and the main difference is just that we're kind of printing out the images. So basically, we're taking in the images, and we're basically going to print two pieces of text on the image. This first command prints the text above in the top left corner. This text is going to be in like a bright yellowish color, and the second command prints the text in a dark black color, and basically what the predicted breed will be is in the top, and the original breed will be in the bottom. So you can kind of check your code as you go. And everything is going to be written to the test results current file. So I've already ran this, and I have our test results current right here. So this is the test that we currently ran. So I think this came out to around 40%, but our best test results were actually ran, I would say, like an hour ago. So we can go ahead and look through our best test results real quick. So when we open the file, we get to see the predicted name in the top left corner and the correct name right underneath that. So you see this one is wrong, so we're going to keep going. This one's also wrong. And there's a correct one. So far we have one correct. We'll just keep going through. Correct, 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 correct. Correct, 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 correct. Yep, and that's about 30 photos that I just went through. And I think when I counted it last, it was about 13 out of 30, which comes out to around 43%, which is pretty good in my opinion for the first day of making the neural network. Of course, with more training, the neural network should get better as we go, and utilizing different optimizations and different algorithms, along with just like, messing around with parameters overall. Overall, this was a really challenging but fun project. I really learned a lot about neural networks and computer vision. I had quite a few challenges and obstacles throughout the course of this project, including learning neural networks from scratch, along with using Python for the very first time. As said earlier, I would like to incorporate my work into an app that would let you insert your own photos and put it on the Play Store for download. If I could change anything about this project, it would definitely be to actually have team members in my group. That would be amazing. Finally, I would also like to thank my PM Tanish, who stuck with me throughout the entirety of the project through communication issues and the steep learning curve of neural networks. Thank you so much for watching my video.